Hoy lo va a presentar Megan Kramer, que es una estudiante de doctorado en Florida, cuyo director es Mauricio Arias, que está aquí de sabático, trabajando con nosotros. Y bueno, Megan es ingeniera civil, titulada en 2018. En 2020 se une a la Universidad del Sur de Florida, en Tampa, a través de una beca de NSF durante unos años, en donde pues adquirió experiencia interdisciplinaria con antropólogos y científicos del mar costero para pues abordar temas complejos, ¿no? De las comunidades costeras. Ahora pues sigue en el doctorado y a través de USF Signature Research Doctoral Fellow, sounds very, very important, y, y bueno, entonces está desarrollando y evaluando modelaciones numéricas para cuantificar la mitigación de las inundaciones y los beneficios que eso conlleva en los humedales y manglares de la costa. Y pues relacionado eso con las estrategias de resiliencia costera. Thank you very much, Megan. Then please, all yours.
Is it working now? Okay, great. Um, Hello, thank you for having me. Sorry, I don't know Spanish, so please bear with me. This will be in English. But I'm very happy to be here today. Again, my name is Megan Kramer. I am a PhD candidate at the University of South Florida in Tampa, Florida. And today I will be sharing with you a little about my ongoing research. So this talk is titled Integrating Nature with Coastal Infrastructure for Urban Flood Protection. So for this talk, I will start with some introduction, go through my project background, and then detail some of my methods, share some early results, and some brief conclusions. So over 1/3 of the global population lives within 100 kilometers of the coast, exposing many coastal communities to coastal hazards that include flooding, storm surge, and erosion. I'm sure you are all very familiar with these hazards, living so close to the coast and studying these coastal processes. Traditionally and typically, to protect these coastlines from these hazards, gray infrastructure is often built. So this includes our seawalls or bulkheads, groins and jetties, and then breakwaters. We also recognize the ability of natural ecosystems to provide some natural protection of the coast. So that includes our coastal wetlands, our oyster reefs, and our coral reefs. Now, along this spectrum from gray to green, in the middle, we have hybrid solutions, which involve components and elements from both. And so that's what I'm really interested in, is the hybrid coastal infrastructure. Hybrid coastal infrastructure has the potential to support ecosystem health while also protecting high-risk urban communities and the ability to implement long-lasting and cost-effective solutions. So now for some of my project background. My study site is located in Palmetto Beach, Tampa, Florida. So this is where in Florida Tampa Bay is. And then up in the north part of Tampa Bay is this Palmetto Beach community. Palmetto Beach is located on McKay Bay, which has the Port of Tampa to the south, and then also the Tampa Bypass Canal flowing into it from the east. This bypass canal was constructed in about the 1960s after a major hurricane caused a lot of flooding in the city of Tampa when the Hillsborough River flooded. And it's believed that some of these dredging activities for the bypass canal caused some of the water quality issues that we see in McKay Bay. So now I'll zoom in to this area, the Palmetto Beach community and DeSoto Park. So here we have the residential area of Palmetto Beach, and then here is DeSoto Park. This is a very highly used park by the community, and bordering this residential street and the park is a crumbling seawall. So you can see very much of the seawall has broken parts like this, exposed rebar. It's kind of dangerous and it needs to be replaced either with another seawall or with something. And here is another visual of this area looking from the north. So because of these water quality issues and damaged seawall issues, the community is interested in improving this shoreline, as well as USF architects and engineers and experts from environmental nonprofit organizations from around the Bay have provided some of their expertise from the environmental side. And also now the city of Tampa is taking on this shoreline improvement project. This site is really ideal because it has opportunities for improved storm surge flood protection, improved water quality, additional green space, more recreational opportunities, and improved park safety. So for this reason, it is really ideal for my research, and I'm interested in how can mangroves be combined with seawalls to reduce coastal flooding. And I hypothesize that in subtropical coastal areas, a hybrid coastal wetland with seawall design would improve flood control compared to either a vegetated zone or seawall alone. Now I'll go through some of my methods. So this work has combined some field work and some numerical modeling. The fieldwork is to characterize the environmental conditions in the bay and verify the model. And the numerical modeling is to evaluate hybrid shorelines under storm conditions. So for some of the fieldwork we've conducted in the bay, we deployed a long-term pressure transducer for almost a year, which we deployed right here. And this helped us to measure water levels, and that included during one major flooding event, which was Hurricane Idalia in 2023. We also got some short-term data during a deployment of an acoustic Doppler velocimeter collected right here for a period of about 2 weeks, which we were able to use for calibration purposes. So here we measured water levels and velocities. We also took some vegetation surveys. So there's 2 shorelines that we conducted some transect vegetation surveys and quadrat surveys. So for the transect survey, we measured the circumference of each mangrove root within 1 meter of a transect line at 10 centimeters and 30 centimeters height above the ground. So this photo is showing this. If you can see this, it's really small, but this orange line here, that was our transect line, and then a 1 meter PVC pipe that we used to have a 1 meter width for our transect. We also estimated the % ground and canopy cover at each instrument site. So we had 1 meter square transects at one end of the transect and at the other, and we estimated these parameters. And then this is just an example of our fieldwork sheet. Next, for our model setup, we coupled the Delft 3D flexible mesh flow model with the Swan wave model. The flow model has a water level type boundary, and the grid resolution, because it is a flexible mesh, ranges from about 4 meters here on the coastline of interest out to about 30 meters. and it has over 83,000 elements. It includes wind forcing as well as precipitation. And that 8 kilometers is supposed to be for this photo. The wave model you can see is in gray, surrounds the flow model. The flow model is the colored area where the bed level is showing. So the wave model has a grid resolution of 30 meters and over 48,000 elements and includes the same wind forcing. So you can see we have a pretty small domain. The domain of the wind model, the length is only 8 kilometers wide. And so in the bay, this distance, this maximum fetch is only about 2 kilometers. Next, for vegetation modeling, in our model, the mangrove vegetation is represented as uniform cylinders. They are two-dimensional depth average bed roughness that is updated based on the local water depth. And that is calculated using vegetation height and density, which again, we measured in the field. Here's a photo from in McKay Bay of some red mangroves. You can see they're accumulating oysters, and there's actually some black mangroves growing behind them. Our vegetation model uses the Baptist 2005 formula, where there's the initial term for non-submerged vegetation based on water depth, and then N is our term based on stem density and stem diameter. If vegetation becomes submerged, then this additional term is included. And this is just a schematic showing the horizontal flow velocity profile and how it changes when vegetation becomes submerged. Here's a simple coupled model schematic. We see that we have the hydrodynamic model. It interacts with the wave model every 30 minutes. It also interacts with the vegetation model. It updates the bed roughness coefficient based on water depth, and the bed roughness coefficient is passed back to the flow model. The vegetation parameters are also included in the wave model, but it is static, not dynamic, so it only goes one way. Now I'll explain my experimental setup. There was 3 main variables that I was interested in here. So we varied the mangrove width from 0 to 50 meters. We also varied seawall crest height from 0, 1 to 2 meters. And then so far we've simulated 3 different storm events for these different configurations. So in total, there's 54 total combinations, which means 54 simulations. Here are some example images depicting what these different configurations look like. So for instance, A shows 50 meters of mangroves with 1 meter of seawall, which we simulated for all 3 storm events. Or for B, we have just 10 meters of mangroves with 2 meters seawall for all 3 storm events. You can also notice that for D, that is for the 0 seawall scenario, and we had to regrade the slope so that it had a realistic slope representation instead of a wall. To simulate storm conditions in our model, we added storm surge through the water level boundary forcing, just using historical time series data, because Hurricane Idalia and Hurricane Helene, we have data for these storm events at our model boundary. For Hurricane Ian, this is actually a hypothetical storm. This storm did not cause flooding in Tampa Bay. It caused a lot of flooding further south in Fort Myers, so we imposed the data from there onto Tampa Bay. We also applied a uniform wind speed and direction and precipitation as well. And you can see the different intensities of these different storms. Hurricane Idalia had the lowest peak storm tide, whereas Hurricane Helene had the highest peak storm tide. And Hurricane Ian had the greatest wind speeds of 26 meters per second. Now I'll share with you some results. So our model was calibrated based on a 17-day period where, again, we had data in there. And so you can see here in the black is the observed water level and red dashed is the simulated water level. We had a good match. We also validated this model over a 14-day period, which includes Hurricane Idalia, so a significant flooding event. Again, observed and water levels are depicted here, and we have another good match. We also got the chance to collect some data when Hurricane Helene hit just last year. I'm sure you guys are familiar with this storm. So before the storm came, I went out and put out 4 pressure transducers inland. So we were able to capture some flooding data. So pressure transducers A, C, and D were inland just behind a seawall. And pressure transducer B was in front of a seawall in a mangrove patch. So we collected pressure measurements every 5 seconds during the storm, which is shown in the black lines in these plots. And we had a good match with our simulated water levels once again during a major hurricane event. Now I'll show a short movie showing our simulated water depth during this storm, where the dark blue is the bay, similar to up in that photo, and the light blue is on land. So when it gets darker, that means that it's flooding on land. And so this is going through the storm event every 2 hours. And so the red transect line, or that red line there, I don't know why it moves. There we go. That red line is one just example transect line that I've selected for analysis purposes. I'll have multiple of those, but this is what I'll use for this presentation. It spans from in front of the mangrove to behind the mangrove. And that red triangle, that's my selected analysis point for this presentation. And it's the same red triangle as up on that image. Also, please note that you may have seen in previous photos, there was a pier here. We've removed the pier for these purposes so that we can have straight shorelines. Okay, so now for some really early results from this project. If we compare the scenarios with no seawall, 1 meter seawall, 2 meters of seawall, and the water levels, we see that the peak water level for all configurations are essentially the same. Same goes with the differences in mangrove forest width. These are all actually plotted here, and they're nearly identical. So what we're seeing so far is that the peak water level is not affected by the seawall height or the mangrove forest width. You'll notice this water level goes down lower. Again, that's because the shoreline was regraded for the 0 meter seawall scenario. But also notice that the 2 meter seawall scenario the water level takes longer to recede, indicating that there may be some potential drainage issues. If we zoom into one of those plots and try to see if there's any difference This shows for the 1 meter seawall scenario, the differences in mangrove forest width, the impact on the peak water level. It's less than a fraction of a centimeter. Now, if we look at the impacts on wave heights, we start to see some differences. So this compares again, no seawall to 1 meter seawall to 2 meters seawall. These are all on the same scale, but without a seawall, the transmitted wave height on land is much greater than for the other scenarios. We also see that within the seawall scenarios, so where we have, for instance, here over 0.4 meter seawall or significant wave height without any mangroves, once we have just 10 meters of mangroves, we see almost a third of a meter of wave height reduction. But from 0 meters of mangroves to 10 meters of mangroves at that same location, there's a pretty big difference. Now this plot plots the incident significant wave height, which is just in front of the mangroves, versus the transmitted wave height behind the seawall on land, whereas the this dashed line is the 1-to-1 ratio, which would indicate no dissipation, and anything above it is no dissipation. Anything below this line is more dissipation. So here we see where there's no mangroves. I've circled this area. We see that there's a little bit of dissipation in significant wave height, but there's a lot of difference. They're very spread out between the no seawall or the 1 meter or 2 meter scenario. Once you have just 30 meters or 50 meters of mangroves, we see much more dissipation, and the difference between 0 or 1 or 2 meter of seawall is decreased. So it doesn't matter very much once you have enough mangroves. The influence of the seawall matters less on the transmitted significant wave height. So finally, to wrap up some of these early results, as I mentioned in the last slide, increases in mangrove forest width reduce inland wave heights. That's to be expected. But importantly, as the forest width increases, the influence of seawall height on waves decreases. Also, mangrove forests up to 50 meters so far show minor effects on peak flood depths during a major storm event. And last, seawalls of 2 meters provide some flood depth reduction of only about 4 centimeters compared to 1 meter of seawall, but pose potential drainage issues. And finally, I'd like to acknowledge a few people, including my major advisor, Dr. Mauricio Arias, and the Watershed Sustainability Lab at USF. Also, I would like to recognize the Palmetto Beach community, which is where this study is taking place. And lastly, my funding from the USF, from USF. So thank you. I welcome any questions or feedback. Thank you for your time and for having me.
Thank you very much, Megan. Very, very nice project. Any questions? Preguntas?
Thank you, Megan, for your nice presentation. I have a couple of questions. One is regarding the calibration. Did you find the same calibration parameters independently of the event you use, or they were different because you have different storms, right? And the other is regarding the wave modeling. If in SWAN, did you incorporate the reflection from the seawall in the model simulations, or not, or is just assuming that everything goes progressively and no reflection? Thank you.
Thank you. Yeah, for the calibration, I think you're asking whether I had to use different calibration parameters. The main calibration parameter was the bed roughness coefficient that I had to tweak. And yeah, that was useful for any of the storm events that I simulated. We got a good match for any of them. So yeah, that was the main calibration parameter. And then for the wave modeling, yes, the waves are reflected or are able to be reflected in the SWAN coupled wave model. I haven't analyzed that yet, the influence of that, but I know that the modeling is capable of that because there's in the wave model, I'm able to put in obstacles that that are reflective. So that's what I use for the seawall scenario.
Thank you.
Thank you for your presentation, Megan. I have a question about the calibration of your model. You have results of data from field, only with the wetland, with the vegetation and the seawall. Yeah. Then how do you calibrate, or is enough to make the model with your proposed the combination of both with the data from one of them, the vegetation and structure is correct, or how do you decide is your data or your results are good?
Mhm. Yeah, so our thank you for your question. Our data collected during Hurricane Helene, I think, provide a lot of confidence in our results. I shared, let me go back to that. Okay. So during this storm event, we were able to put a data logger in the wetland and then also a data logger on land right here, which allowed me to simulate a combined forest with seawall. And we saw a good match with our results, and that was using the same vegetation model. So this helped give me confidence that if I have this sort of combination elsewhere, that that would give a relatively good representation of that system. At the same time, I know I'm varying a lot of hypothetical scenarios, right? So I can't test all the different configurations in the field, but this gives us more confidence that it's representing the roughness well, and it's representing a seawall well, and it's giving the right amount of flooding inland. But it is challenging with these major storm events to get the right, to get really good data to use for validation, right? So I was excited about this data. Okay. Yeah.
Okay, thank you.
Alejandro.
Hi, Megan. Thank you for your presentation. So if I think I understand what you show us today is that basically mangrove is like very good for containing storm surge or flooding, right? Like to stop the wave height. So in that sense, I guess, um, thinking about costs or time consuming, like I think I don't know if you're like trying to say that it's better to have these hybrid options, right? Like having good and healthy mangrove forests, but also in places where you already have taken the mangrove away, you can build maybe a seawall, because how much time for a mangrove forest will take to be healthy enough, or I don't know how high it needs to be to really make those considerations, right? Like, I don't know if it's a small mangrove will have the same effect on stopping a flooding, and it will be faster, but maybe not cheaper to build a seawall. So I don't know, that's more or less what you're trying to say.
Yeah, that's an interesting question. It kind of gets into the next step that I was really interested in taking with this research, which is conducting a life cycle cost analysis, which would dive into all this, right? Looking at what is optimal for, cost efficiency and for flood protection and for the environment. So I haven't dug into that, but from the just flood protection side of things, yeah, I think, the important thing is just to be above the, anything that's at risk should be above the peak flood level, right? So you could just construct a seawall, but that won't necessarily have, there's a lot of side effects to that too, right? You will have maybe another erosion problem, which is costly and you have to fix. Or that needs to be maintained when it is crumbling like it is here. So for a quick fix, a temporary barrier, would maybe protect from some flooding. But these hybrid solutions, I think, are more sustainable, and that's what we're interested in here. Yeah, the mangroves are showing wave height attenuation, but unless the soil is above the peak storm, it's not going to reduce the flood depth. But we saw the difference between a 1 meter and 2 meter seawall also didn't reduce the peak flood level. So yeah, it's just important to be above the storm surge, I guess. Yeah.
Teresita.
Hi, Megan. Your presentation was really interesting. And my question is, you listen to it? My question is that if all the 54 scenarios that you have, are you considering the sediment transport there? Or, I don't know, the sediments that are being trapped in the roots? Or the slope in the beach is, I don't know, you cannot track all the sediments because of the slope?
That's a great question. That is not being considered here, but if I had another PhD to do, maybe I would tackle that. We've seen just in my last couple weeks here, I've learned about how much sediment is trapped in these mangroves around Sisal, right, during these big Nortes events. So I think that would be really interesting to track. I think we've seen less of that in Tampa Bay, less sediment accumulation as rapidly. But yeah, that would be super interesting to track because we know that they kind of can build ground and maybe even keep up with rising sea levels. So yeah, I think that would be super interesting to add on to this project. Yeah.
But now you're only changing how dense is the vegetative data, right?
Yeah. Mm-hmm.
Okay. Thank you.
Thanks.
Wilmer.
Thanks, Megan, for your presentation. I just have a doubt. Could you tell us, please, a little bit about how do you create the wind fields? Which wind parametric did you use? Because I see in your validation the match is very good. So I think that if you use a historical event, do you have the opportunity to compare the winds from your wind model with the historical event in the storm? But that was not part. Thank you.
Yeah. So if I understand correctly, you're asking if I've compared the wind from my model with the data.
Yeah.
So I'm actually using the data for my wind in my model. So I'm using for the storms, Idalia and Helene, which impacted this community very much. There's a wind station not far away. So I just use that data, updated every about 6 minutes. And yeah, I downloaded the wind speed and direction and just applied a uniform wind field. And so since my model domain is very small, just less than 8 kilometers, I think it was justified because there's not that much variation at that one spot. Yeah.
Thank you.
Thanks.
Hi, thank you. I just have a quick question because right now you are doing this validation with hurricanes that produce waves, like really high waves, right? So that's the point of having the sea wall, if I'm understanding. But what if you, what will happen if the flooding is not because of the waves, but it's because it's just raining a lot without wind? It's not producing anything in the ocean. Like, for example, if you have like atmospheric river or something like that, that's not that common in Florida, but it may happen. So I'm just wondering if you have a really high seawall and you have the flooding just because of rainfall, if the seawall is going to produce a negative effect because it's not going to allow for the water to go to drain. So if that's a consideration that it's something that you're considering?
Yeah, that's a great question. It's definitely something I'm considering now after seeing these earlier results and with the water level receding so slowly with the 2-meter seawall. I think I'll look into that more and make sure that that's being represented properly. And yeah, it is interesting because there's different benefits and harmful impacts from these different scenarios. So yeah, I will consider that, I think, with the 2-meter seawall and some of the potential negative impacts, because our model does represent precipitation. I think for Hurricane Ian, which was that middle intensity storm, that one had a lot of rainfall and the waves were actually directed a different direction in the bay. So now that I've finished all those simulations, I think that would be a great case study for those types of impacts. So yeah, thank you.
Thank you, Megan. There is a question online. In the Riviera Maya, which is in the Quintana Roo coast and in the Mexican Caribbean, a lot of development is taking place on the coasts where there are mangroves that are not protected. What scenario do you see with a change of land use for this tourist construction? What do you think? I don't understand very well the question, but I believe that what will be the impact of destroying the mangrove that is not protected?
Yeah, well, I think what we're seeing here is that the big widths of mangroves are really reducing the wave heights. So I see potential negative impacts there. If they're developing this area and putting up seawalls, that's not only destroying a lot of habitat, but it's going to, the mangroves are also protecting the seawall, which is another element here, reducing the loading and prolonging lives of seawalls. So yeah, I think, I'm not sure how to answer that one. I don't know what they will plan to do, but.
And you mentioned that at some point you may try to put some numbers, no? What would be the cost of restoring versus what you gain by putting this mangrove, etc., you will see the cost benefit at somehow.
Yeah. If I have the time and the the ability to do it, I'm really, this was part of my project proposal, was to look through this full life cycle cost analysis, because it's hard to just look at these one variable or two variable results of flooding, because these are all so these systems are so interconnected, and there's a lot of impacts, not only immediately, but down the line. So I would love to do some more analysis into that, to look at the sustainability of these options.
That's nice.
Yeah.
Here we have Patricia Huereca, who is an expert in life cycle and this kind of analysis. Maybe you can have a chat with her.
Okay, thank you. I would also, can I add one more thing? I think I could have elaborated on this a little bit further too, but I'm looking at these solutions in very urban environments where there's space limitations, right? So if you have a natural coastline where you have the ability to have kilometers of mangroves, I think that's great. There's not the space for that here. And so part of the motivation for this project is, how can we add more green into the gray? Because we can't necessarily always just take out a seawall. There's so much development already here. So trying to figure out, can we add more green to the gray? Yeah.
That's great, thank you. ¿Más preguntas por acá? ¿En línea? ¿No? I have a few questions. I sent them to you, but when you show the scenarios, no, in slide 21, you don't show a 4-meter mangrove and no seawall, but I think that in your results you work on many more scenarios, right? But you don't have the 50-meter mangrove without seawall, at least here. Did you model that?
Yes, you're saying 40-meter mangrove?
No, the 50-meter mangrove without seawall.
Oh, yes.
Yeah, you
Yeah.
have it, right? Okay.
Yeah. Sorry, these are just, examples, but.
Okay. And for the 10-meter mangrove, is the 4-meter resolution of the numerical mesh good enough, or you would need a better resolution?
That's a great question. Yeah, so the resolution is it's not the same everywhere, right? But we did a good match. So it's roughly, these aren't necessarily exactly 10 meters, but they're roughly about 10-meter increments based on the triangular mesh. So I could, increase the resolution ×2 or whatnot, but that's at the cost of computational efficiency, and we don't expect the results to change very much.
Okay.
But it would be a good exercise to,
maybe.
do that. Yeah.
Let's see. Why do you think the water level, you showed that the water level doesn't change much with or without mangrove, or with or without seawall, right? It's only a few centimeters. Why do you think is that?
Good question. Yeah, I've been pondering this too. I think, water finds a way, whether it's a little crack or whatever, but these aren't physical, especially the mangroves aren't physically completely blocking anything. So water is able to get through. What they're better at is reducing that wave energy, which is what we're seeing with the wave height reduction. Same thing with the seawall. We're simulating a very realistic context. This is not the most idealized experiment. So water is able to get around no matter what, kind of. So water finds a way. It's what we're seeing is the energy is being reduced due to these two systems.
Good. Okay. And one more last question, more in the coastal engineering side. The seawall is vertical, right, in that place? And in your hybrid scenarios, maybe it would be interesting to also modify the seawall design. No, when there is a slope, the dissipation is better, the reflection of the wave decreases a lot, and even when instead of a wall you have rocks, no, also it dissipates a lot. Then maybe this could be another scenario if there is time, and if you think it's
Yeah, yeah, that's a great point. I definitely have the ability to tweak some of these design choices. Yeah, maybe you and others have some advice there. This was kind of keeping the experiment as simple as possible with all these different variables happening. But I could add those options on. I think the sloped wall could be really interesting too, because as you know, a seawall reflects almost all energy, and that could also pose potential issues for mangrove recruitment. So I think that would be a good option to look into next. Yeah, thank you.
And just one more, sorry. Anybody else? Bed roughness. How do you determine the bed roughness? From literature?
So the vegetation, based on the vegetation model, the bed roughness is calculated based on those vegetation parameters. So if you remember the formula, I'll probably go back. So this C is the bed roughness coefficient, and it's calculated based on these vegetation parameters, height, density, and diameter, which I averaged based on the measurements I took in the field of mangroves that are living already in McKay Bay. So yeah, so this bed roughness coefficient is calculated based on these vegetation parameters.
Yeah, and it doesn't vary on time.
It does
It
based
does?
on the water depth. So
Yeah.
H
Yeah.
is water depth and H. So that's how the flow model is interacting with this vegetation model. It's giving it the water depth, and it's passing back the bed roughness.
I see. Okay, that's fine. I think that's it for me. Thank you very much. Someone else? ¿Alguien más? Well, I think, thank you very much.
Thank
Megan.
you so much for having me. Yeah. Yeah, I appreciate you guys.